Okay, so today we're going to begin talking about probability distributions. And there we go. So this is section 5.1. And we've got, as is typical, we have a lot of definitions that we have to talk about first. So the first is a random variable. Which is a variable that has a single numerical value. Determined by chance, so hence the random part. For each outcome. So when we look at random variables, what we end up with are probability distributions because the excuse me, since the values are determined by chance, that comes up with a probability that becomes the single numerical value. And because we have multiple outcomes, we then need to organize them. So we do that with a probability distribution. And a probability distribution is usually in a table. It could just be a description, but usually they give it to us in a table. And what it does is it gives the probability for each value of the random variable. Within random variables, we have subcategories as well. We have discrete random variables. Which is a collection of values that are finite. So this should make sense because we talked, very early on in the course about discrete data and continuous data. So it's the same idea here. If your random variable is discrete, that means that the values are finite or countable. So it has values that are finite or countable. When we have a continuous random variable, then that means that the collection of values are not countable because there are infinitely many. So it has infinitely many values. Which means that they are not countable. So, an example that we used a lot at the beginning of the course with continuous data was temperatures, because we can just continually be more and more specific. You know, we can do 98.6 degrees, 98.62 degrees, 98.625 degrees, so on and so forth. So we can't really count how many different values there are for temperature. There's going to be an infinite number. Within a probability distribution, one of the things you're going to need to be able to do is to identify whether or not something is a probability distribution or not. So we have some requirements. So requirements of a probability distribution. So the first one is that it has to have a numerical random variable x. So if you see a distribution where the data is qualitative or categorical, that's not going to work. It has to be numerical or quantitative data. So it has a numerical random variable whose number values have, not has, I said have and wrote has for some reason, have corresponding probabilities. So meaning that each possible value has its own assigned probability. The second requirement of a probability distribution is that when you look at all the individual probabilities and you add them up, the total needs to be approximately 1. So we'll just write that the sum of all the probabilities equals 1. Now, if you get 0.99999 or 1.0001 or something very close to 1, that's going to be okay, because as we talked about before, there's sometimes like just rounding differences where it might have caused that to be the problem. But we know that the total probability of all the situations that are available has to be 1, because it's a 100% chance that one of the choices is going to happen. So if you have a distribution and the total is not 1 or extremely close, then it is not a probability distribution. Total has to be 1. Next requirement is that every individual probability has to be between 0 and 1 itself, which really, if you satisfy the other requirements, this should kind of naturally happen, but each of the probabilities themselves has to be between 0 and 1. So for every individual value of the random variable. Now, I think that the reason why they put this in here is just in case someone would have a table where they would have like negative values and the total was 1. So it's just stressing that each individual value has to represent a probability and the total of them has to equal 1. All right, so that's the requirements to have a probability distribution. We also have probability histograms. And a probability histogram looks just like your other histograms. So we did frequency histograms, relative frequency histograms. Now we have probability histograms. And a probability histogram is very similar to a relative frequency histogram. It's just a histogram where our vertical scale shows probabilities. So the example that you saw in the book, let me bring it up real quick just to illustrate. Here was what you saw in the book. So notice you've got all the bars, no spaces between the bars. I don't know why. This is from probably a computer diagram. When we draw it, it would, the scale would be right next to here. There wouldn't be a gap here. But notice our vertical scale is probability. It's labeled as such. So number of heads from 2 coins. Obviously, the lowest number of heads you can get is 0. The highest number you can get is 2, and it's just showing the probability of either of those. So that's what a probability histogram would look like. One thing that's important to remember is that when we are looking at a probability distribution, and I'll just put this by with stars just as something to remember, that with a probability distribution, we are describing a population because the distribution has all possible values of the random variable. So because we're describing a population and not a sample, you have to remember that that means that when we go to calculate various values, such as the mean or the standard deviation, that they are the parameter version of those. So we're not looking at X bar and S, but rather looking at mu and sigma. And when we write out the formulas here, we will reflect that. So we're dealing with populations, which means that we're using parameters. So from a probability distribution, you are going to have to be able to calculate the mean, the variance, and the standard deviation. So the formulas that they give us, so this is mean, mu for the population mean. What you do with a probability distribution is you take the sum of each value of the random variable, because that is X, multiplied by that particular random variable's probability. So X times P of X, and then you add all those together. That's what the sigma means. So that's your formula for finding the mean. For variance, they give us 2 different formulas. And as always, I don't care which way you do it. Whatever makes more sense to you is totally fine. So variance is sigma squared. And we can find that 2 ways: by taking the sum of each random variable's value minus mu squared times its probability, or we can take the sum of X squared times P of X and then subtract mu squared. Again, does not matter which you do. Whatever you find easier is totally fine. The book says that this guy is easier for manual calculations, which is what we'll be doing. So we'll probably use this one, but this one is also fine. In fact, actually, I think I used this one in most of my manual calculations just because it made more sense. So either way, as long as you've shown the work, I'm not going to be picky about which formula you've used. The standard deviation is then going to be the square root of the variance. So standard deviation is the square root of the variance. So once you've found the variance, then you need to take the square root to find the standard deviation. Okay, another thing that we need to talk about when we are talking about random variables is expected value. And when we have expected value of a random variable, what we're talking about usually has to do with when we have a situation where you can either win money or you can lose money. So when we talked about odds back earlier in a previous chapter, same idea. So a lot of the expected value problems have to do with gambling, or it could be with, a situation with a business where you have expected profit versus loss. But what we do with expected value is actually the same as calculating the mean. So for a discrete random variable, it's equal to the mean. So expected value equals the mean, which means we calculate it the same exact way as we did over here. We take every possible value that there is, multiplied by that value's probability, and then add them all together. Now, I do want to show you that in most cases, for expected value, I'm just going to use the same example from the book here because I have that. But if you bet $5 on the number 7 in roulette, then in this case, there's only two values of the random variable, one where you get the number 7 and one where you do not. So the probability of losing the $5 is 37 out of 38 because there are 38 slots on the roulette wheel. The probability of making a net gain, so you win, you get $175 back, is 1 out of 38. And it tells you here the prize is $180, so net gain is $175. So in a betting situation, there are only two possibilities, win and loss. We can find expected value for any situation. It does not have to be a betting situation. But here, for the roulette, this shows organized in a table. Here's the values of the random variable. You can either lose or you can win, which again, in order to be a probability distribution, they have to be numerical values. So we can't just write lose and win. We have the numerical values that go with them. So the numerical value associated with losing is that you go down $5. The numerical value associated with winning is that you go up $175. So if I want to find the expected value, we take x times p of x for each possible outcome. So -5 times 37 over 38, which gives you this. Then the other possible outcome is winning 175. Probability of that is 1 out of 38, which gives us this. And then again, it's the sum of those. So I add x times p of x for losing to x times p of x for winning, and I get negative 26 cents approximately. So the expected value for getting the number 7 in roulette with a $5 bet would be negative 26 cents. So meaning you're going to lose more than you're going to win. So every time you go up there, you're expected to lose 26 cents on average. Okay. So next thing that we need to discuss definition-wise are our significant values again. So we've already talked about this and done this exact definition, but when we have probability distributions, the way it looks is a little bit different. So we're going to write out the same definition, but the way we're going to apply it is a little different than before with other probabilities, excuse me. So we have significantly high, which we say that X successes in N trials is significantly high if the probability of X or more, so of greater than or equal to X, is less than 0.05. So if you add up all the probabilities of X or more and it's less than 0.05, then having X successes is considered significantly high. Likewise, significantly low same idea. X successes in N trials is significantly low if the probability of X or fewer, so less than or equal to X, is below 0.05. We use that 0.05 threshold a lot. So if X successes has that low of a probability, then that means it's significantly low or significantly high, depending on which probability we're looking at. Also want to remind you that if we don't have this probabilities, if we're not looking at a probability distribution, then we can still use range rule of thumb, or significantly high would be mu plus 2 standard deviations. Significantly low would be mu minus 2 standard deviations. So those would also be value thresholds as opposed to probability thresholds. So if we have either of those, that would also designate significantly high or significantly low. Okay, next we're going to look at some examples of probability distributions and how to calculate the mean and standard deviation, how to determine if something is significantly high or significantly low. There are some problems in your homework that are just definition based. So we're not going to do examples of those. Those you should be able to read the definition and determine. So it'll ask, what is the random variable? Is it a discrete random variable or is it continuous? It'll give you tables and ask if it's a probability distribution. So meaning you'd have to look to see if it meets all 3 requirements, so on and so forth. So we're just going to do examples that require the calculations. So let me type out our first one here. All right, so here's our first example. We have a table. It shows the number of times that a newborn baby's crying wakes its mother after midnight in a week. We are going to find the mean and the standard deviation. So while you are writing this down, again, just to reiterate that if I were asked if this was a probability distribution, I would be looking at those three categories. So first of all, do I have a discrete random variable that has a numerical value? And I do. All of the values of x are numerical. Each of those values has a associated probability. Each of these values are between 0 and 1. And then the third thing that would have to be true is that the sum of all the probabilities would have to equal 1. So that's probably why the writers of this problem didn't reduce the fractions, because it makes it easier to determine whether it's equal to 1 or not if you can just add up all the numerators rather than having to type all the fractions into your calculator. But 2 plus 11 is 13, plus 23 is 36, plus 9 is 45, 49, 50 out of 50 total, which is 1. So this is a probability distribution, which means that we can do all the calculations necessary to find the mean and the standard deviation. So I'm going to go ahead and start with those calculations. So if you're still like writing it down, maybe pause the video if you need to. I generally like to just add columns over here for the values that I need, and then add them all up. So for mean, our formula says that we're going to take x times p of x for every value and then sum them, so add them all up. So I'm just going to make an added little table over to the side, and I don't know why I changed, you can see it, I changed the color, trying to make it blue, but it is not letting me, so I guess everything's going to be the same color today. So what I'm going to do then is I'm going to take a x times p of x for every value in my table. And then at the very bottom, I'm going to write out the sum. So this down here is where I'll write the sum. So x times p of x means 0 times 2 out of 50. So 0 times 2 out of 50, which of course is 0. Then I've got 1 times 11 out of 50, which is 11 out of 50. Sorry, my 1 kind of connected there. Then I've got 2 times 23 out of 50, which is going to reduce the denominator, so I've got 23 out of 25. Or if you prefer to write it 46 out of 50, that is fine also. So then 3 times 9 out of 50, which gives me 27 out of 50. 4 times 4 out of 50, which you can either write as 16 out of 50 or 8 over 25. However you prefer. And then 5 times 1 out of 50, which gives us either 5 over 50 or 1 over 10. So they gave us these probabilities in fraction form. That's not always the case. A lot of times they'll be given to us in decimal format, so don't assume that they're always going to be fractions. Much of the time they're going to be decimals. So to find the sum of x times p of x, I'm going to be adding all of these together. So if they have the same denominator, I can certainly do that with the denominators. So if I go back to thinking that these are out of 50, then I have 11 plus 46, because that was 46 out of 50 originally, plus 27 plus 16 plus 5, which gives us a total of 105 out of 50. Now, you can also simply, type in, the 0 times the fraction and add up all the decimal equivalents. That's totally acceptable as well. Obviously, you should get the same answer regardless. But this one actually comes out as exactly 2.1. So that is the mean. So our mean value for number of times that a newborn baby's crying wakes its mother is 2.1 times. So we can write that down here. Mean is 2.1 times. Remember, our rounding rules for mean and standard deviation are usually one decimal place past the original data. Now, since our original data is in fractions, that would be different. We'd have to write them out in decimals, but this one came out nicely to exactly 2.1 anyway. So our mean is going to be 2.1 times. Now we're going to find the standard deviation, which takes a bit longer. And I looked back at my homework, and I do typically use this top one. Again, if you prefer and understand this one, you are certainly welcome to use it. So what it then does is we take x minus mu, and then we square it, and then we multiply that times the probability. So that's going to add quite a few columns over here. The first of which just being the x minus mu squared. Our mu is 2.1, so I'm doing 0 minus 2.1 squared. And then I've got 11 out of 50 minus 2.1 squared. And so on down the line. So 23 out of 25 minus 2.1 squared. Then 27 out of 50 minus 2.1 squared. 8 over 25 minus 2.1 squared. And finally, 1 out of 10 minus 2.1 squared. Now, what we have to do with that, according to our formula, is we have to take that guy times p of x, so times the individual probability. So x minus mu squared times p of x. Now again, p of x is this original guy over here. So we're really taking this times, in this case, the probability, which was 2 out of 50, and then so on down the line. Now, I usually press this all into my calculator just like this, just because you don't want to round in between because that's going to make your answer slightly off. So when I do this, and I'll show you here in a second once I finish writing all of these individually out, oh my gosh, I made a horrible mistake and I just now realized it. Oh, that's bad. Okay, so in here, for some reason, I just looked at the wrong column when I started here. So this, I didn't use the x's, I used the p of x's. So I'm glad I realized that before we typed it all into the calculator. So sorry, there's no way to fix it on the video without actually re-recording the entire video. So we're just gonna fix it here. So 1 minus 2.1, 2 minus 2.1, 3 minus 2.1, 4 minus 2.1, and 5 minus 2.1. Yikes. Okay. So we'll fix those over here as well. Here we go. Okay, so the p of x's are that second column, and so now we're going to multiply each of those times its individual probability. So now that I've got the right thing actually in there, can multiply times their probabilities. So I'm writing this out so that you'll know what to write out on your paper. Now, you do not have to do it in table format. In some of the homeworks, if all it asked me for is the standard deviation, then I probably am just writing this plus this plus this plus this, so on and so forth. So you don't always have to organize it in a table if that's not your personal preference. Four out of 50. Oh my gosh, today is just the day of mistakes too. I also used the wrong column there. That p of x is 9 out of 50. And then 5 minus 2.1 squared times 1 out of 50. So this is what I'm going to do in my calculator because that sum is going to be my variance. So get out your calculator here. Let me find mine. There we go. And I'm going to move it down a little so that I can see. Actually, I might move it over to the side because I have to be able to type. But I'm just going to type in this entire thing exactly as it is and add them all together. So if you want to take a minute to go ahead and enter that in your calculator while I am doing that, I'm going to move this over so I can see it, and you then can see what I'm typing. So x minus mu, quantity squared, times that x's probability, which is 2 out of 50. And so that's for 0. Then I have to add that because, again, the variance is the sum of all of them. So then I do the same thing for the value of 1 and times its probability, which was 11 out of 50. And then go to the next one. So 2 minus 2.1 squared times the probability of 2, which is 23 out of 50. Then next one, value is 3, so 3 minus the mean squared times the probability of 3, which was 9 out of 50. Then 4, so 4 minus the mean squared times the probability of 4, which was 4 out of 50. And finally, the last one, value of 5 squared times its probability, which was 1 out of 50. And finally, now this represents the sum of x minus mu squared times p of x. We can press enter, and it gives us 1.05. So that means our variance is 1.05. Now, it didn't ask us for the variance. It asked us for the mean and standard deviation. So that means the standard deviation we're going to find by taking the square root of 1.05. So in my calculator, square root of that answer, which gives us a long decimal. Again, since these were given to us in fractions, what you round to might vary because we're not really sure what the original probabilities were, but the original data themselves are whole numbers, 0, 1, 2, 3, 4, and 5. So we're going to go to the tenths place, which is actually 1.0 when we round it appropriately. So I would say approximately 1 times. So we have a mean of 2.1 times with a standard deviation of 1 time. And that would give us our mean and standard deviation. So next thing that we want to talk about is significantly high or significantly low. So let me type this out here. Okay, so would a newborn baby that wakes its mother after midnight 4 times a week be considered a significantly high number? Explain using the probability rule and the range rule of thumb rule. So again, we talked about in our definition section the 2 different ways that we can determine significantly high or significantly low. So here it's asking us to use both of them. So the probability rule for significantly high, if we look up to where we have, it's if the probability of x or more is less than 0.05. So for the probability rule, in this case, x is 4. So we want to know the probability of being greater than or equal to 4. And so in this case, we can just get those values from the table. So greater than or equal to 4 would just be 4 or 5 in this case. So that probability would be 4 out of 50 plus 1 out of 50, which gives us 5 out of 50, or 1 out of 10, or 0.1. So the probability rule tells us that in order for it to be significantly high, that probability that we just calculated would need to be less than 0.05. So 0.01 is not less than 0.05. So no, because the probability that x is greater than or equal to 4 is not less than 0.05 is what we would write for our explanation, and then this would be our work. So that's using the probability rule. Using the range rule of thumb, significantly high values are mean plus 2 standard deviations. So our mean we just calculated from our table is 2.1 plus 2 times the standard deviation, which is 1.0. So that gives us 4.1. So what this is saying on range rule of thumb is that in order to be significantly high, I have to be 4.1 or greater. 4 is not greater than or equal to 4.1, And so both of our methods agree in this case that 4 times a week would not be considered significantly high, meaning it would not be considered unusual or out of the norm. All right, last example. Let me type it out. Okay, here is our last example dealing with expected value. So why don't you take a minute to write that down? So pause the recording if you need to. All right, so this one's a little different than some of the expected value things that we've done because in this case, you're not like paying up front and then getting money back or not getting money back. So it's just simply saying if you toss heads, you must pay $6. If you toss tails, you get $10. It wants us to find the expected value. So remember that in our definitions, we said that expected value is equal to the mean. So we're going to be doing the sum of x times p of x. So the value, obviously the two situations you have are tossing a heads or tossing a tails. So if you toss a heads, the value that is associated with that is paying $6. So that's -6. The probability of that happening, the probability of heads is 2/3. So this is x times p of x for that value. Then our other outcome that's possible is tossing a tails. The value, the x that's associated with that is positive $10 because you get 10. The probability associated with tossing tails is 1/3. So these are the only two outcomes. So we've done x times p of x for both. We're going to add them together to get the expected value, which remember is the exact same thing as asking for the mean. So -6 times 2/3, our 3 is going to cancel. We get -4 there, plus 10/3 here. So -4 plus 10/3 is going to give us -2/3 or -0.6666, so on and so forth. When we write the answer, because we're talking about money, it's expected value of money, we're going to round that one always to the hundredths place, basically to the nearest cent. So -0.67 cents. So -67 cents is the expected value, meaning that on average, you're losing 67 cents every time you play the game because you are much more likely to lose than to win. So games that have an expected value that's negative, it means, that your chances are greater that you're going to lose. Anything that has an expected value that's positive means that the chance is greater that you would win. All right, I think that should cover everything that is in the homework, which is on the page 195. So you should hopefully be able to do that successfully.